we're going to prove that two functions are continuous at points. So this is going to be using the epsilon delta definition of continuity. Later we'll see another slightly easier way to do this using sequences and limits. But let's get some practice. So we've got a function. Domain is all the real numbers. The function is given by 3x minus 5, and we want to show it's continuous at the point 2, 1. So what do? Well, we set everything up. So we let epsilon be greater than 0. We want to find a delta greater than 0 so that if the distance between our point x and the number 2 is at most delta, so in other words, they're in that strip. If you haven't watched the earlier video with the animation, I really recommend you do that. So in other words, if we're within that strip, strip centered around 2 on the x-axis, then when we look at the values, the distance between them will be at most epsilon. So if we go through some arithmetic, we just substitute in f of x and f of 2, and when we simplify, at the end we see that we just get 3 times this quantity x minus 2. And so remember, we're in charge. We want to find a delta. And so our goal is to choose delta, and it can be any number we want. And we want to know that if x minus 2 is smaller than that number delta, then 3 times x minus 2 had better be smaller than epsilon. Well, seems like if we let delta be epsilon over 3, then if we multiply it by 3, then that would be smaller than epsilon. And this is going to be the proof. So on the next slide, I'm going to do everything again, sort of in an abbreviated form. This is kind of like the template we've had before. So for this problem, we'll let epsilon be greater than 0. I like to use the word declare, so I'll declare that delta equals epsilon over 3. And then I claim that if x minus 2 in absolute value is less than delta, well then, and I just work it out. F of x minus f of 2, blah, blah, blah. There's a bunch of algebra. We get down to that 3 times x minus 2 absolute value. And now we get an inequality. We use the fact that x minus 2 in absolute value is less than delta. And we use the fact that delta equals epsilon over 3. And so we've done exactly what we wanted. If x minus 2 is at less than delta, then the difference in function values will be smaller than epsilon. So now is a good time to maybe pause this video, maybe go and look at one of the homework problems and try to work out the details of that on your own. We're going to move on and do a quadratic function next. So we're going to prove that the function given by x squared minus 2x plus 2 is continuous at the point 3, 5. So we'll see these are a little bit more involved, and there's a couple fun ideas that we'll get to work on in here. So again, we want to let epsilon be greater than 0. And again, our goal is to find a delta so that if x minus 3 is at less than delta, then f of x minus f of 3 will be smaller than epsilon. So we carry through the arithmetic as before, just substituting the function and the value. And we, in the case of quadratics, it will always happen that we'll be able to factor it. And if you notice, we have this x minus 3 factor here, and that's also showing up over here, right? And that will always happen with quadratic functions. But here we have to be a little bit careful, right? Because if we just do the same trick and let x minus 3, say, be, well, what would it have to be smaller than? We'd like to say something like maybe epsilon over absolute value of x plus 1, but then the question is, what is x, right? X is not a constant. And what we have to declare a constant number for delta. So we're sort of stuck at the moment. But the idea of this is really useful in analysis. Remember, as long as we can name a delta that works, we win. Right? We don't get any bonus for finding the optimal delta. And in fact, the smaller the delta, the smaller the delta, the better. Right? Because if we know it works within a range of 1/2, but we only go within a range of 1/4, of course it's going to work, right? As long as we make the number delta smaller, it will still work for our purposes. So we need to remember that we're in charge. And so why don't we agree that we're going to choose delta less than 1, right? So let's just agree straight away that we'll always choose delta less than 1. And how is that helpful? Well, if we go back a slide, we've got this if statement here. We're going to know that x minus 3 is smaller, and that's probably going to take care of this left-hand factor. But this x plus 1 factor is a bit more problematic. So this is where it's going to come in. So if I choose that x minus 3 in absolute value is smaller than delta, and we all agree that delta is going to be smaller than 1, then that means that quantity x minus 3, well, since its absolute value is smaller than 1, I know it has to be sandwiched between 1 and minus 1. And now I'm just going to force that this x plus 1 property in here, I'm going to force that that means that x plus 1 has to be between 5 and 3. Right? So if I've just added 4 to all 3 parts of this inequality, so I add 4, I get x plus 1. So it's add 4 over here, I get 3. I add 4 over here, I get 5. And this is a technique. This is the first time you've seen it. This is something you'll get practice with on the worksheet we'll do on Wednesday, and also on the homework. So in any case, that means that x plus 1 is always between 3 and 5. So if we take the absolute value of it, it's always going to be at most 5. All right, we've got something that's going to be smaller than 5. And so what that means is if we choose that delta less than 1, and we choose x minus 3 less than delta, then if we go through that process, we factor f of x minus f of 3. Remember, it factored as x minus 3 times x plus 1. That's going to mean it's smaller than 5 times x minus 3. Right? So now we're in good shape, because now we say, well, we really wanted this to be smaller than epsilon. And what I knew was that this quantity x minus 3 was smaller than delta, so I could, if I pick that to be epsilon over 5, then this would cancel and I'd get epsilon. Well, that's great, right? So that's the idea. We've got all the pieces in here. This part here that I'm kind of circling with the mouse, that's going to be sort of our scratch work. You'll see me refer to it in the next slide. So anyways, let's just tie everything together. We've got our function. The proof is really short once we've got everything together. So we're going to let epsilon be greater than 0. And then we're going to let delta be any positive number smaller than both epsilon over 5 and 1. Right? So again, we could just actually let delta, say, be the minimum of the two. It would work. And I've color-coded them. I've got red and blue to sort of show you where those numbers are going into the proof. And so if we go through the proof, right, if x minus 3 is smaller than delta, well, then that means it's smaller than 1, since we chose delta smaller than 1. And so by our scratch work, we're going to get that x plus 1 in absolute value is going to be at most 5. So now let's go through. So now we do f of x minus f of 3. Remember, it factored as x minus 3 times x plus 1. And that's going to be, well, x minus 3, that was smaller than delta. And then x plus 1, that was smaller than 5. And then now we're using the fact that delta is smaller than epsilon over 5 to fill in this quantity here. And then everything cancels and we get epsilon. So in the end, we've shown that we've found a delta. We specified what it was. I mean, in this proof, we said it could be anything. You could just take it to be the minimum. And we've shown that if x minus 3 is less than delta, then f of x minus f of 3 is going to be less than epsilon. So thanks for watching these videos. Now you're in a great position to get started on the homework.